Hello, Chemistry 12 AP. This is Mr. Chan. And what I wanted to do today was I wanted to revisit a couple of the Le Chatelier shifts that I worked on last day for my Chemistry 12 AP, for my Chemistry 12. But what I wanted to do was I wanted to focus a little bit on the AP material. Okay, so the first one I wanted to touch base with you is talking about change in pressure. Now, back in the last lesson with this grade 12, what I did was I only focused on the increase or decrease of pressure or the change in volume and how that affects equilibrium. What I want to talk about with you folks today is there is another way that we can change the pressure, and it is by adding a non-reactive gas. So in this particular case, if the change in pressure is due to an addition of a non-reactive gas, what happens is there will be no shift in the equilibrium. Okay, so if the change in pressure is due to an addition of a non-reactive gas, then there will be no shift in the pressure and the equilibrium. This is due to the fact that even though the pressure is higher, the partial pressure or concentration of each substance has not changed, so an equilibrium shift is not required. So in this particular scenario, this equilibrium that I gave you from the last lesson, notice the reaction is hydrogen and oxygen gives you water molecules. If we were to add something like a neon gas or an argon gas, nothing that affects this particular reaction, yes, the pressure has increased because you've added another particle to it, another substance. But because the neon or the argon have no direct effect on this particular equilibrium shift, you haven't changed the amount of hydrogen, you haven't changed the amount of oxygen, and you haven't changed the amount of water. What happens is that there is no equilibrium shift. Okay. Now, on the back side of your notes, what happened is, let me get rid of this here. What happens is there's a more detailed explanation. So if you take a look, it says, when increasing the pressure, why does it favor the side of fewer particles? Now, if we were to focus solely on the number of effective collisions, so rates and stuff like that from our previous unit, what happens is when you increase the pressure, both the reactants and products have increased. All right, and therefore you have more effective collisions, both in the forward and the reverse directions. But the increase of effective collisions for hydrogen to oxygen, in this case, for the forward rate, has increased more than the percentage of effective collisions of the reverse rate. So because of that, what you get is more products or the forward reaction are made or favored initially. Okay, so in this particular case, both the reactants and products have increased in concentrations, and therefore both of them have increased number of effective collisions. But because the percentage of effective collisions for the forward rate of hydrogen plus oxygen has increased more than the percentage of the reverse rate, therefore more products are made or favored initially. Okay, now you might say, well, I don't get it. Well, the example would be like this. Let's say we take the gym. Okay, so let's take our school gym and let's say we had 60 students. And we take the second school gym and we take 10 students. Now, if we were to squeeze the students of 60 into half the gym and take the 10 students and squeeze them into half a gym, the percentage of the concentration is increased in both. The chances of an altercation occurring when there are 60 students versus if there are 10 students in the gym being squeezed has gone up dramatically. So that is what was meant by the number of effective collisions has increased more. Both of them, the concentration would go up, but for the gym with 60 students, the chances of effective collisions or altercations has gone up more than a gym of 10 students. Conversely, when decreasing the pressure, why does it favor the side with more particles? Again, both reactants and products have decreased, and you generally have less collisions. But the percentage of effective collisions, or the forward rate, has decreased more than the effective collisions or of the reverse rate. And so what happens is more reactants or reverse reactions is favored initially. Again, if we take our example of 60 students in a gym and 10 students in another gym, if we were to expand the space, the 60 students would be able to spread out more. The chance of altercation goes down. The 10 students, if we spread out their space, yes, they're able to spread out more, and their chance of altercations also goes down. So both of them have gone down, but the percentage has gone down more dramatically for the one with higher particles. Okay, and that's what the highlighted in blue is talking about. So because the number of effective collisions for the more particles has gone down more dramatically, the rate decreases a lot more. Okay, and so that's why the reactants are favored. Now, for the temperature shift, why does increasing the temperature favor the endothermic reaction? Again, it has to do with rates. Both the forward and reverse rates have increased, but the endothermic reverse rate has a greater percent increase than the exo or forward rate, or the forward rate, or the reverse rate speeds up. Therefore, initially, the endo reverse rates is initially faster than the exothermic or forward rate. Now, I'm sorry I kind of bumbled through it, but the idea is this. When you talk about increasing the temperature, both the forward and the reverse rate go up. So the exothermic direction and the endothermic direction both go up. But when you increase the temperature, the endothermic reaction, percentage-wise, has a greater increase than the exothermic rate. And so therefore, this is why it favors the endothermic reaction, because initially it would be faster. Why does decreasing the temperature favor the exothermic reaction? Again, if we take a look at rates, both the forward and reverse rate decrease, but the endothermic or reverse rate has a greater percentage decrease than the exothermic or forward rate. Therefore, the exothermic or forward rate is initially faster than the exothermic forward rate is initially faster than the endothermic reverse rate. So when we take a look at this, if we decrease the temperature, both the forward and the reverse rates go down. But what happens initially is that the reverse rate, or the slower reaction, in this case the endothermic, slows down a lot more than the forward or the exothermic reaction. And so therefore, initially the forward or exothermic reaction is faster. So that's why when you decrease the temperature, the exothermic reaction, or in this case, the forward rate, is faster. All right, take some time to digest that. If there are issues, please come and see me. Now, some of you might say, well, Mr. Chan, can we just memorize what you did for change in pressure and change in temperature, like what you did with the grade 12? Yeah, that's not a problem. If you need to get it through initially, not a problem. But my recommendation is when you are going through this, are you able to relate it to, whoopsie here, Are you able to relate it to the rates and what's happening to the forward and the reverse rates relative to each other? All right. Thank you very much. Have a good day. Bye-bye.